planetary system that breaks all the rules. Colliding worlds reminds us of the formation of the moon. A super solar storm hit Mars too, and an explanation for a 7-hour gamma ray burst. All this and more in this week's Space Bites. Think about the distribution of planets in the solar system. We've got all of the terrestrial planets, Mercury, Venus, Earth, Mars, close up to the sun. Then you've got the gas giants, Jupiter and Saturn, and then you've got the ice giants outside of that. And it's expected that that is what you will find when you look out to other exoplanetary systems. Similar thing. Think about the planets that are closest to the star, right? They're forming in this protoplanetary disk. You've got these intense solar winds coming from the star. This is blowing away a lot of the lighter volatile chemicals. You're left with the rock, the metal. That's what comes together to form those planets. Then farther out in the solar system, we had the volatile elements be able to come together, the ices, the ammonias, things like that, and you get the gas giants. And then farther out, say beyond the asteroid belt, you've got places where the hydrogen, the helium, the various lighter elements can come together, and that's how you get the gas giants. Further out, you get the water, ammonia, things that would be ice here on Earth if it was that cold. And that is expected, that's what we find in the solar system. Therefore, that is what we expect to find out there in the universe. And of course, the universe does things that we were not expecting. And so now astronomers have found an example of a planetary system that seems to break these rules. It's called LHS 1903. And it was discovered several years ago, and astronomers have found 3 planets in this system. So you have a rocky planet close up to the star, and then 2 sort of mini Neptunes, so like dwarf gas giants. And that seemed normal. Okay, great. That follows that standard distribution. And now astronomers have found a 4th planet, and it's rocky. And so now you've got rocky, gas, rocky, which is weird and not expected. So how did it get this rocky planet outside of where the gas giants are? Well, maybe it did just indeed form in place, and that our understanding of the way planetary formation isn't correct. Another possibility is that it formed closer in and then migrated out. And we know migration happened in the solar system. And maybe it was going to be a dwarf gas giant, dwarf gas giant. Maybe it was going to be a dwarf gas giant, but then it was starved of gas. So all the gas had been used up for the other 2, and so there was none left for it. So it's an interesting story, shows that the universe can do things that we weren't expecting. We've got a story about this from David Dickinson. Astronomers have found yet another Earth-sized world orbiting around a red dwarf star. And, we know of quite a few of these. We're still waiting for that first detection of an atmosphere of a Earth-sized world orbiting within the habitable zone of its red dwarf star. That hasn't been found yet. But in this case, you've got a planet. It's got a little over 1 Earth radii, and it only takes about 1.55 days to go around the star. So it's going quite quickly, and it's relatively close. And so its average temperature is 525 Kelvin, which is 251 Celsius. So that is very hot. And so it's expected that the atmosphere for this planet is going to be long gone. What's interesting about this star, which is designated TOI 4616, is that when astronomers went back through archival data, they found that they actually had this star image continuously back through the 1950s. So we have decades and decades of observations of this star. And they can then measure the changes, the variations in brightness over time to see how, are there a lot of flares, a lot of radiation being pumped out by this star. And so this planet is like right at the edge of where they may or may not be able to hold on to its atmosphere. And so this gives astronomers a sort of perfect world to be able to explore these ideas of atmospheric escape, atmosphere volatility, composition of the planet. Sort of this planet will probably be the ideal world to compare against sort of other planets to find out, what is the likelihood of finding atmospheres around planets that are orbiting around red dwarf stars. So I'm sure there's going to be a lot more observation on this one just because we have such good archival data of its star as well. Got a story about this from Evan Goff. So astronomers think they've found a planetary system where 2 planets recently crashed into each other and have created huge clouds of dust in the system. And this research came from looking through archival data from the Gaia mission and some other sky surveys, and they turned up this really interesting star. Its output for the longest time was nice and flat, and then starting around 2016, it had 3 flashes where it changed in brightness. And then in 2021, it changed significantly in the optical spectrum. And then astronomers did follow-on observations in the infrared to see what that looked like. And what they found is that while it was flickering in the optical side, it was just growing a lot brighter in the infrared side. And so in this case, brighter means that there was hot dust, hot rock in this system. And so the story that the astronomers think happened is that you had 2 planets that were very close to each other. They were spiraling around each other, and they were starting to kind of tear chunks of each other apart. And this started to create some dust, and that led to those dips in brightness that they saw earlier on. And then finally they collided, and you got just this big kind of explosion of rock and dust. And this is an analogy for the event that probably created the moon, that there was 2 large planet objects around our orbit, the proto-Earth and then this other object, Theia, and that they probably got closer and closer to each other until they got caught up in the mutual gravity, started to tear tidal tails apart from each other, made this mess, and then finally they merged together, and the debris is what turned into the moon. So it might be that we are watching the formation of the moon in another star system. We've got a story about this from Alan Boyle. Asteroid mining is still this very theoretical concept. There are a lot of companies that have been working on it in the past, have gone out of business, other companies that are working on the idea right now. And one of these companies is called Transastra. And their plan is that they want to go out to find an asteroid that is in the sort of 10 to 20 meter range, sort of the size of a house, something that's about 100 tons. And then bring that asteroid back to probably the Earth Moon L2 Lagrange point. So a place which is relatively stable, a place that we can access. And their plan is to essentially put a Kevlar bag around the asteroid and then be able to use their thrusters to be able to pull this asteroid back to this stable location. And they propose that if they could go out and get a bunch of them, they could start to just kind of pile them all up together like this rubble pile asteroid made by people. And then you could mine this for water and other elements to be used for exploring the solar system. They got a $2.5 million grant from NASA to be able to create a 10-meter version of this bag. And they've identified about 250 candidate asteroids that are sort of meet this size and have the right kind of trajectory that they could be brought back into this location. Now, there's reporting from Eric Berger over on Ars Technica about this. The moon doesn't have a global magnetosphere in the way that the Earth or Jupiter does. Instead, it has these local regions of magnetic field. And a lot of this is remnant magnetism left over from when it did have a magnetic field and then it had lava flows that were charged in one direction or the other. It also has induced magnetic fields coming from particles coming from the sun that interact with the surface of the moon. You would expect with these magnetic fields that they're as powerful as they are, right? Like whatever is the amount of magnetism that's in the rock, that's the magnetic field that you get. But for spacecraft orbiting around the moon, they've detected that these magnetic fields can change and can actually extend significantly far away from the surface of the moon. And so how is this possible? Well, researchers have been running simulations and they think they've got the answer. And it's this mechanism called the Kelvin-Helmholtz instability. And have you ever seen clouds in the sky where there's some kind of like wave-like formation in the clouds, and the clouds look like kind of rolling waves in the sky? And it's a similar thing like that, where you have different speed winds that are going past each other, and you get this shear in between that causes these vortices along the clouds where the winds are coming together. And so the researchers did simulations and found that you can actually have magnetic fields do something kind of similar. You've got the solar wind that's coming from the sun. It's interacting with these magnetic fields on the surface of the moon. You've got different speeds of solar winds, which are magnetized, and they are running against each other. And you're getting these vortices that are starting to form from where the solar winds are interacting with the surface of the moon. And then these can make these magnetic field lines extend out and be detectable by the spacecraft while they're orbiting around the moon. What's really interesting about this research is that it's probably happening on Mars as well. And so we could probably detect that with spacecraft at Mars. I've got a story about this from Andy Thomaswick. Every week we do a vote on our channel where you tell us what you thought was the best story of the week. And the winner last week was that there's a new measurement for the age of the universe. So thank you everyone who voted last week. We're going to put this week's vote into the post tab here on our YouTube channel. So go there, vote early, vote often, and of course, subscribe to the channel, click on the notifications bell, vote on every poll that you can see, and then that will encourage the algorithm to send you more of these. About 2 years ago, in May 2024, the world got a treat. And this was a very powerful solar storm hit the Earth, and we got auroras around the planet. I was traveling in Japan, but my wife saw them and she said they were just mind-blowing. And people were seeing them as far south as Mexico. So it was a great time for auroras. And it turns out that that solar storm that hit the Earth also hit Mars. Like, it just happened to be the way things were lined up that Mars got similar activity. And in fact, there were 2 spacecraft at Mars that were able to do a bunch of measurements about this. The ESA's Mars Express and the ExoMars Trace Gas Orbiter. And according to their measurements, if you were at Mars, you would experience 200 days worth of radiation in just 64 hours because of the solar wind. And that should feel a little unsettling, right? Like, if you're in a spacecraft traveling from the Earth to Mars, then you would have gotten 200 days worth of radiation in a little over 2 days. And so what they did was the 2 spacecraft were communicating with each other as they were just going over the horizon from one another. And so they were able to send their radio signals through the upper layers of the atmosphere and then measure how the signals were refracted by the atmosphere, and then use that to measure essentially the density of the atmosphere as it responded to the solar storm. And it also created this dramatic increase in electrons at 2 various altitudes in Mars, sort of at 110 kilometers and about 130 kilometers altitude. And so it just shows that even when you're all the way out of Mars, these solar storms can be significant. And this is something that, future explorers on Mars are going to have to be wary of. I've got a story about this from Matt Williams. Gamma ray bursts are crazy. So in a fraction of a second, and one of these exploding objects can produce more radiation, more energy output than the sun will put out in its entire 10 billion year lifespan. And normally, gamma ray bursts are extremely short. They just last a fraction of a second, a couple of minutes at the most. But in 2025, astronomers watched a gamma ray burst that lasted for 7 hours. And it actually released 3 distinct blasts as it was going through this process. And then it left an afterglow that lasted for months. So it had all of the characteristics of a gamma ray burst, and yet it was unlike anything that had ever been seen. And so it gave off a lot of the same kinds of radiation as a gamma ray burst, but just behaved in this really weird way. So what caused it? Well, there have been lots of papers, people trying to speculate on what caused this gamma ray burst. And a new paper says, well, maybe this was a star being destroyed by an intermediate mass black hole. So, we know of the stellar mass black holes, the ones as star goes supernova and die. We know about the supermassive black holes that are at the hearts of galaxies, but there's this sort of very rare class of black holes in between called intermediate mass black holes. In fact, they should be everywhere. Like, how do you get the supermassive black holes without these intermediate mass black holes? This is one of the big mysteries, but some have been found often at the centers of dwarf galaxies. And so this star probably got too close to an intermediate mass black hole, and then the 3 separate bursts that they detected, that was it, tearing off chunks of the star bit by bit until finally the star went right in and was just obliterated entirely by the intermediate mass black hole. Got a story about this from Mark Thompson. There are 2 dwarf galaxies that you can see if you live in the southern hemisphere. They're the large and small Magellanic Cloud. And I've seen them once in my life. I was in Australia. I was able to see them. It's pretty amazing. They look like clouds, I guess. Yeah. They look like clouds, hence the name. The small Magellanic Cloud is a bit mysterious. It lacks a lot of the features that you see in the Large Magellanic Cloud and in dwarf galaxies in general. It doesn't have this really smooth rotation of stars around the center of the galaxy. It has this big, long tidal tail that is stripped out behind it. And it has this very strange irregular shape. Like, it doesn't even look even slightly spirally. And now astronomers think they figured out why, which is that at some point in the past, the small Magellanic Cloud just plunged right through the large Magellanic Cloud. And that would explain all of these things. It would explain the tidal tail, the sort of disruption of its structure as it was approaching the larger galaxy, why it doesn't have stars in this sort of more ordered fashion. They're all just jumbled up inside the galaxy. These are the kinds of things that would happen if it hit the large Magellanic Cloud. And then this might help explain some of the weird features in the large Magellanic Cloud. Like it has this bar structure at the center of the cloud, but it is tilted out of the plane of the galaxy. And so at some point in the ancient past, the small Magellanic Cloud just like did a bullseye right through the large cloud. Got a story about this from Carolyn Collins Peterson. I hope you're enjoying this week's episode of Space Bites, but you probably had to suffer through an ad when you watch it. Like obviously some of you use ad block, some of you are YouTube Premium, but some of you had to watch an ad. And we can't turn those off. YouTube won't let us. And we can turn off the mid-roll ads for now. I don't even think we can turn off the ads at the end anymore. And this is just the reality of using YouTube. Well, there is a place you can go where you don't have to watch any ads for any of our videos, and that is over on Patreon. Now, to encourage you to go and try out that experience, we're going to make another version of this video, but with one extra story. And this week's extra story is about how astronomers have found thousands of stars that are actually very similar to the sun in the Milky Way. So I'm going to put a link down in the show notes. You can go watch it there. You don't have to pay anything. You don't have to be a subscriber. You don't have to be a patron. You can just watch it for free with no ads. And of course, if you want even more stories, we're covering probably 30 to 40 stories over on Universe Today this week across a range of topics. And that's too many for us to cover here in Space Bites. But I gather all of the stories up into my weekly email newsletter. I write every word in it. It's completely free. There's no ads. Go to universetoday.com/newsletter to sign up. I've been talking quite a bit about how you can use AI to create like various data visualizations, and someone wanted to know why I'm recommending that. I'll give you an answer in a second, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Barry Lake Roofing, Brian Bodu, Caradwin, Chuck Hawkins, Commander Baylock, Cooper Nelly, Dark Finger, David Gilton and David Matz, Evan.pro, Greg Feely, James Clark, Janice Smith, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org, Ren Kaidu, Richard Williams, Sean Sargent, Stephen Fallon-Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zelda Board Galactic Defender who support us at the Master of the Universe level, and all our patrons. All your support means universe to us. So we love the Snorks asked, why do you keep advocating for people to use AI instead of learning to code? So I think for the first time in history, we have coding tools, these AI coding tools that get the job done, that you can express the task that you want, and then you can iterate with these coding tools like Claude Code or OpenAI's Codex and have software that actually performs this function. And, you know, I have a degree in computer science. I learned to code. And that process, when you first start out learning how to code, it is really tough. You have these great ideas in your mind and what you want the code to be able to do or what kind of application you want from the software. But in many cases, the learning curve is so steep that a lot of people are discouraged. It can take you hundreds, thousands of hours to be able to get to this place where you're able to actually make some of the things that you want. And you still, even when you're like good at what you do, which I never became great at this, you are limited by just the amount of time that you have, that you will very slowly make something that does what you need. And if they're like throwaway ideas, things you want to test out, ideas you want to try and implement very quickly, you're looking still at days, if not weeks or even years of work to be able to accomplish something. And so I think that, you know, it splits into these sort of two camps. There's the people that really want to learn to code, and for them, learn to code, like absolutely. But there's other people that are just like, I just want software to do something. I want to solve a problem in my life. I want to explore an idea. And you can now do this without having to learn how to code. And I think that's fine. When I think about all of the other methods of AI, how it's being trained on people's intellectual property, coding is the one where it is more like math, more like having a chess computer play against itself. Produce code until the code does what it's supposed to do. I don't have the same ethical concerns about people using AI coding tools in the way that I would for people, say, doing AI art or AI video, things like that, or even AI writing. And I really think that there's a lot of people who you have that there are bespoke tools or tools that you could create for yourself, ways to interact. You're enthusiastic about how you can try to visualize Gaia data. You can do the visual side. You've got lots of great ideas, but you can't actually implement the code. And this is a way that you can start to do that. And what you find is that you do have to go in and start to learn more about how the nuts and bolts of your computer works, how the file system works, how the code bases work, how dependencies go, how to set up a virtual environment. Like, you start to do all of the things using Git. And then you come back and you start to actually look at the code, try to make sure if it's producing problems in the Python code that it's developing. And eventually you can decide, do I want to keep learning more? I want to become a coder, or do I want to just hang back and let this be able to create software? The thing that's most important, in my opinion, is to really understand that line between making things for yourself in a safe sandbox environment that it's not going to try to be out there on the internet, versus creating things that you are trying to make for a general audience, for the public. Like, there are security issues, there's privacy issues. It's next level for you to be able to create what you think is commercial software using this vibe coding. But if you're just making stuff for yourself, I think it's a great way to go. And like, I have replaced many of the software as a service tools that I had been subscribing to create something that is exactly what I need for the exact kinds of tasks that I need. And I think it's a great time to try experimenting with this kind of stuff. All right, we'll see you next time.